All right. Okay, chapter 7, there's going to be a lot of conceptual things here where I'm going to try to relate what you're hearing. This is abstract. This is thermodynamics. I didn't put that term on there so it doesn't scare you away. But physical chemists, chemists divide themselves up into like organic chemists, inorganic chemists, analytical chemists, a chemist that focuses on laboratory analysis kind of things, physical chemists, biochemists. But a physical chemist, really, this is the physical chemist's area of focus. Energy, reaction rates, equilibrium. And it's a little bit more abstract. There is math involved, but the math is beyond the scope of this course. So I'm going to, most of it. Some of it that does relate and we are going to apply, I'll point that out to you. But there is a lot of math, but it's deeper math. It's more physics oriented. But so here's going to be some of the key concepts in here. Reactions and energy. Thermodynamics. Whether a reaction is endothermic or exothermic. Does it release energy or use energy? There are some laws. There's the first law of thermodynamics, the law of conservation of mass and energy. That's the first law. These terms, enthalpy, entropy, I'll explain them. Entropy relates to the second law of thermodynamics. This is the calculation you'll deal with, is calorimetry. Okay, that's all thermochemistry, energy related. Then you shift a little bit down to here. Kinetics has to do with the rate of a reaction. How fast does a reaction proceed? Kinetics. And then we'll talk about equilibrium and Le Chatelier's principle as it relates to equilibrium kinds of situations. And actually, this is very relevant to the body. Your body is about, a couple thousand equilibria working with each other. Metabolic pathways, different concentrations of this, that, and the other thing. Very, very complex. All right, let's look at the energy side of things. And this is important. I mean, it was a chemical reaction that got you here this morning, most likely. You came in a car or bus or however you got here. It was burning some kind of fuel, gasoline, diesel, whatever. And you've already seen this. Here's octane plus oxygen. You're already familiar with this part of the chemical reaction. A hydrocarbon like octane with oxygen forms carbon dioxide and water. But you don't put gasoline in your car because you want carbon dioxide and water. You put it there because you are harvesting the energy that's associated with the octane and the oxygen. So this is where chapter 7 focuses. We start looking now at the energy changes that are occurring in a chemical reaction. And they're vital. I mean, the news is just full of talk about energy. Wind energy, solar energy, the price of oil, this, that, and the other. Energy is all around us. We're paying for it. You fill up your car with gasoline, you're buying this chemical. Yeah, I like to point this out to people. It is a chemical reaction that runs your car. Yeah, you got a radio, you're getting electricity. Where's that coming from? Well, your generator, where's that coming from? The engine's turning, and it's turning the generator and producing the electricity. Everything behind the movement of that car and the function of that car and the heat you're getting from that car is coming from this reaction. It's coming from a chemical reaction, and you're harvesting this energy, converting it into work to move the car, converting it into electricity to run your radio, converting it into heat, which you don't need in August or July here, but it's converting it into heat. All right? So If you burned the gasoline in a drum, you would get heat. You'd get it'd be all heat. 1% of work, what's it doing? It's pressing down on the earth. The earth doesn't really feel it. But that's what it's doing. There's a little bit of force pushing down on the drum, which doesn't cause the earth to go out of its orbit or anything. But a little bit of work being done there. But you put it in an internal combustion engine, you do get heat. You got a radiator in the front of your car to handle the heat. There's a lot of heat. But what you really want that gasoline to do is work. You want it to do work. Move the car. And it is doing that. How's it doing that? It's working on those pistons inside that internal combustion engine. It's forcing those pistons down. Now, if it wasn't doing that, it would just be converted to heat. It'd be all heat. But you're getting some work out of it. Now, if you want to become a billionaire, double that amount of work that you get out of it. All right? You'll be a billionaire. All right? Steve Jobs would be envious of you if you can just double the work. And Southwest Research, they have people over there really trying to do that. How do we, maybe not double it, but how do we get more work and less heat out of an internal combustion engine, and therefore more gas mileage? All right, thermodynamics, the study of energy, work, and heat applied to chemical change. Basic concepts of the kinetic molecular theory. Kinesiology, you go study kinesiology over in Wasatch. What are you talking about? Movement, dynamics, kinesiology, muscles, kinetic molecular theory. The theory of the movement of molecules and atoms. What's going on? They're in constant random motion. They frequently collide with each other. Only some collisions, those with sufficient energy, will break bonds in molecules. Let's stick with our gas analogy. You go to the gas station, you put the tube in there, and you can see a little bit of the fumes coming out of the gasoline. The gasoline is mixing with oxygen. Oxygen is bumping into the gasoline molecules. If you fill your lawnmower with gasoline, you have gasoline and oxygen. You think, oh man, doesn't that stuff explode? Well, at that temperature, as long as you don't have a static spark or anything, they are bumping into each other, but not with sufficient energy to cause them to react. They just bump into each other. Bump, bump, bump. No reaction. Could they react? Definitely. Spark, they'll explode. All right? So what's happening? At a higher temperature, they bump into each other and they break bonds. And they start reacting with each other. So that's what this is talking about right here. When reactant bonds are broken, new bonds are formed and products result. And you have a chemical reaction, and you have either the release. Not every chemical reaction releases energy. We're going to talk about that. We're going to divide chemical reactions into two major categories. Those that release energy, those that absorb energy. Okay, so to talk about that, thermochemists, physical chemists, start kind of talking about a system and what's surrounding the system. The system is the reaction they want to study. So they kind of isolate. I've got something that I want to study in terms of energy change. That's my system. And then surrounding it is the environment, the rest of the universe, the rest of the room, whatever is around that system. All right? Okay, so let's go on. So there's a system and a surroundings. I think this next slide has the same pictures again. So if the system you're studying releases energy, it causes the surroundings to go up in temperature. That's what's happening with your car. Get up in the morning, you touch the hood, it's the same temperature as your garage or your driveway. You start the engine, you come back home after driving for half an hour, and the hood is hot, the car's hot, the radiator's hot. Why? Because the reaction going on in the engine is releasing a lot of heat, heating up the surroundings. That is exothermic. Okay, I want you to understand those terms. So although this is conceptual, some of the definition or working knowledge of these terms is expected of you. So an exothermic reaction releases energy. An endothermic reaction absorbs energy, and there are these two types of reactions, exo and endo. Let me give you a quick example. A cold pack that you can buy. You can buy cold packs and heat pads. All right, you can buy both of them, and you carry them around, and they're at room temperature until you want to use them. And what do? This one says crush it, press it down on a hard surface, put your hand down, crush the thing, and it gets cold. What happens? It's got ammonium nitrate and water, solid ammonium nitrate, and liquid water inside the cold pack in plastic bags, but separated from one another. You press on it, you break the seal between the water and the ammonium nitrate. The water flows in here and dissolves it. It becomes aqueous ammonium, aqueous nitrate ions. It goes into solution, and it absorbs energy. Where does it get the energy? It gets the energy from the water. The water's at, let's say, room temperature is 20 degrees centigrade. It's at 20 degrees centigrade. It sucks some of that heat out of the water to make it go into solution, and the temperature of the water drops, gets colder. So what is that one doing? Here's your system, your ammonium nitrate and your water. You break the seal, it's sucking the energy out of the water and pulls the energy out of it and causes the temperature to go down. It gets cold whenever you want it to get cold. This is a delta H of solution, H being the enthalpy, the heat energy change. A heating pad is working off of a chemical reaction of iron reacting with oxygen to form iron oxide. This was on your exam just right now, balancing that equation, and the answer was 4. Correct coefficient for iron was 4. This is an oxidation reduction reaction. We'll talk about that in chapter 8. But it releases energy. Now notice these two expressions here. Here's a chemical reaction with energy expressed as on the product side. Do you need those? Who needs them?
She's on the calendar and you're not on the calendar. No, sir. And she has an exam.
All right. Sorry. Thank you. Okay. So you can see this energy is coming out on the product side, and this energy is being written on the reactant side. We need to add energy to make this thing happen. We don't need to add energy here. We just need to bring the oxygen in contact with the iron, and this starts forming and releasing that energy. So this is this is an endothermic reaction. This is exothermic. So this is a delta H of reaction. Change, the delta H, or change in enthalpy. All right, so dissolving sodium hydroxide in water. Now, not everything that you dissolve in water requires energy to dissolve. You dissolve lye, this is sodium hydroxide, which is a basic component of lye. You dissolve that in water, it gets really hot. You can bring water almost to the boiling point if you put enough sodium hydroxide in there. I mean, it'll get hot, 80, 90 degrees centigrade, almost get up to boiling. So it releases heat. So is that endo or exo? Exothermic. This is exothermic. You see temperature going up. It's an exothermic. It's releasing energy. That's why the temperature is going up. This is an acid plus a base. This is a neutralization reaction. Temperature is going up. Endothermic, exothermic, exothermic. Dissolving sodium chloride in water. So sodium chloride plus water plus heat forms aqueous sodium chloride. Temperature goes down. What is this? Go ahead. You got a voice. Endothermic. Reaction between nitrogen and hydrogen. Nitrogen and hydrogen forms ammonia plus heat. Okay, a reaction is so slow it does not happen under standard conditions, but that's releasing heat, so that would also be exothermic. Okay, law of conservation of energy. The first law of thermodynamics, or law of conservation of energy. Energy of the universe is constant. Okay, so you won't, if you hear me say this, I don't mean it. These reactions are not creating energy. You've heard me using the word release. The energy is there in one form, and it's being converted to another form. It is, think of it as potential energy stored up in the chemical bonds. There's energy stored in those bonds. And when you move to new bonds, that energy is being released. There's less energy in the new bonds than there was stored in the original bonds, and the net effect is the release of energy. So this is what's happening in chemical reactions. Not all chemical bonds have the same energy value. They differ. All right, so you can come back and read some of these. I'm going through this really fast, and I know it's a lot to absorb, but so that you can come back and read these or listen to the tape, listen to the lecture, whatever, and kind of dwell on it. But just to understand, exothermic reaction, the energy, it will take some energy to break those bonds, but it's less than the energy formed when you make those new bonds. All right, so you make those new bonds and you get a lot of energy out of that's released. And so the net effect, comparing the energy required to break those and released to make those, is exothermic. Endothermic, the energy to release those bonds, takes a lot of energy to break those bonds, more than you're going to get by the bonds formed in the new reactants, the new products. And so that's endothermic. Let's look at that in a diagram, diagrammatically. Again, we're just talking in general here, and then I'll apply this to a couple specific chemicals here in just a second. So here's our reactants. In terms of the energy content of the bonds, there's a lot of energy there. So we break those bonds and we form these new products, C and D, which now there's not a lot of energy in those bonds. And the difference in the energy related to the bonds and reactants and products is the amount of energy that's released. This is the amount of energy released. Well, I guess here is the specific example. Methane in your furnace at home. Methane plus oxygen forms carbon dioxide and water plus 211 kilocalories, and that would be kilocalories per mole of methane in this particular case. You're getting 211 kilocalories per mole. It's written as a negative. So delta H is negative 211 kilocalories per mole. You can see that this energy is coming out on the product side of the equation. Exothermic. So the carbon-hydrogen bonds here, the oxygen-oxygen bonds here have a lot of energy in them. And the carbon dioxide and water are much more stable, lower energy compounds. And the difference in the content of those energies is the amount that's released. You can have a situation here where you have ammonia and you're going to decompose it back into its elements, nitrogen and hydrogen. And it requires energy to get the ammonia. Now we don't have an A and a B, we just have A, ammonia. One thing over here, one reactant. But it's decomposing into nitrogen and hydrogen. These have a lot more energy associated with those molecules than there is associated with the NH bonds in ammonia. And that 22 kilocalories, you can see this is a positive sign. And that is very helpful. The sign of your delta H is telling you whether that reaction is exothermic or endothermic. Endothermic reactions will have delta H's that are positive and exothermic delta H's that are negative. All right, I'm not going to dwell on this. We could go into a deep dive here as to whether a reaction is spontaneous or non-spontaneous. Maybe the example is one I've already mentioned. You're working with gasoline, and we all go into gas stations and we fill our car with gasoline. What are we doing? We're handling an explosive chemical. How are we doing it? At room temperature, or maybe up to 100 degrees, 110 degrees Fahrenheit. All right? Does it explode? No. It is not spontaneous. There's no spontaneous reaction at the gas station. Why? Because of the temperature we are at. We are at a relatively low temperature. But if you were in a different situation, or if you knew that gasoline was mixing with oxygen at a higher temperature, I don't know what temperature that would be, we could look it up. The auto ignition temperature of gasoline and oxygen, or a gasoline and air. Oxygen in the air. But there's an auto ignition temperature. If you had a little container of gasoline and oxygen and you started heating it up, there would be a temperature. Without a spark, there would be a temperature at which, bam, it would explode. Okay? Because it would get to a point where now that reaction would be spontaneous. It's going to occur at that temperature. And so that's what we're talking about. Spontaneous, non-spontaneous reactions. Nitrogen and oxygen are in the air. 80% nitrogen, 20% oxygen. They don't react with each other on a normal basis. Thunderstorm comes through. A lightning bolt goes through. The air has that electricity, that potential electrical difference between a cloud and the earth is there. Huge difference, because it's thousands of volts that's driving that lightning bolt down to the ground. The thunder is the explosion of the air around that lightning bolt. That's what thunder is. The air is exploding because of the heat. It's being heated up to real high temperatures instantaneously, and you start getting all kinds of reactions. You get all kinds of nitrogen oxygen compounds being formed. I don't know what the primary ones are. I'm not studied this in any great detail. But all of a sudden now, what did not happen under normal conditions is happening spontaneously. You're getting these reactions, higher temperatures. All right, so ordinarily, this is not a spontaneous reaction, but there are nitrogen oxygen compounds that can be formed. You ever notice your grass getting greener after a thunderstorm? Farmers like thunderstorms. Why? Produces all kinds of nitrates. The rain washes it out into the ground. Free fertilizer when a thunderstorm comes over. Google it. They'll calculate how many tons of fertilizer a thunderstorm is creating per acre, or per square mile, or whatever. It is free fertilizer. All right, so spontaneous, non-spontaneous. It brings in now this concept of entropy, which we give the letter S. Enthalpy is the letter H, dealing with heat changes. And then we talk about the delta S, the change in entropy. Change in entropy. And what is entropy? It's a measure of the randomness of a chemical system. Entropy can be the driving force behind a chemical change. And a matter of fact, well, let's go back and just, this is kind of a curious little question. If it takes energy to dissolve the ammonium nitrate in water, why does it do it? Why does it dissolve? Has to do with entropy. This is a low degree of randomness. It's ammonium nitrate crystals. It's not very random. There's an ammonium ion, a nitrate ion, an ammonium ion, a nitrate ion. Ammonium nitrate. It's very ordered. Ammonium nitrate crystals have a high degree of order. So let's see what happens when we put water in there. So this has to do with entropy. So we have our ammonium nitrate down here, crystals, highly ordered. I mean, it'd be kind of foolish to compare this to diamonds, but diamonds are highly ordered, carbons in very specific locations. Well, you're not going to go make $1 million selling ammonium nitrate crystals, but they are very ordered. And so now you got water here, and what happens? The water starts dissolving these, and all of a sudden you are increasing entropy. The randomness of the system is increasing. You start out with all water and all crystals down here, and what do you end up with? You end up with a beaker with water and ammonium nitrate ions all over the place, less ordered than they were here in the crystals. You follow me? So that's an increase in randomness, or a delta S change that's positive. Delta S has increased. Entropy has increased. And the second law of thermodynamics says, I don't know if we have it here. Do we have the second law of thermodynamics? I guess we, oh yeah. The universe spontaneously tends toward increasing randomness. That's the second law of thermodynamics. That the universe will tend towards disorder. It will move towards disorder, not order. I only have to look at my office and my desk to be reminded that entropy, that there's a second law of thermodynamics, saying that things want to get more disordered. And to order them, I gotta do work. You have to do work on a system to overcome that tendency for greater entropy, increasing entropy. Okay, here's an example. They can't see that real well. There's a flask right here. I don't know. I don't think. Okay, can you see that? There's a. I don't know if you can see that. Can't hardly see that. I can see it beautifully right here. Looks great. Just really got washed out on the screen. Or at any rate, you got a flask here. With a valve right here. And so let's imagine that we've put a perfume in this system right here. We've got air here, we've got air over here, but we have this nice fragrance locked up in this side of the container. And we open that. Oh, everything went away. Great. And we open that valve, and what happens? Spontaneously, this perfume molecules diffuse over into here to where they end up being same concentration on both sides of that thing. They do that spontaneously. Why? Because this is, delta S is positive. Just think about this. There is some order here. There's air, there's perfume. There's no perfume over there. There's some degree of order there. There's less here. It is more random. The perfume has diffused out through the whole thing. We no longer have a side of this flask where there is no perfume. All right, we don't have that distinction any longer. It has spontaneously gone that way. And maybe to wrap your mind around it a little bit more, if we started with that, and then we opened this valve, you wouldn't ever get this. You wouldn't get the air saying, oh, let's all, or the perfume saying, let's all go over there. Okay? Come on, everybody over here. No, they don't do that. They bounce around and they're randomly in both things. So that actually would require some work. If you wanted to gather all of them back up, they talk about herding cats, okay? This is that analogy. What do the cats do? Well, they go by the second law of thermodynamics. They each go in their own random different direction. But you want to herd cats, you got to work at it. Let's get all these cats together. Takes work. Okay. The universe spontaneously tends towards increasing disorder. All right, so we can talk about whether if the disorder increases, then the entropy has increased. So let's look at 3 examples here. Simple examples that you're aware of. Let's take ice. So you got an ice cube here. Got an ice cube sitting in a beaker, and it melts. Which one is more orderly system, and which one is more random? Okay, the ice is more orderly. The water molecules are locked in a crystal structure, and water has a very specific crystal pattern to it. But the water, let's see, anybody have a water bottle? Let's see, Michelle, you at least have a drink there. Okay? Or water, drink. All right? Look, that has a certain volume to it, but look at it, has a certain randomness to it as well. You move it around and it changes its shape. It's conforming to the shape of the container. The ice cube won't do that. I move this around, the ice cube doesn't change its shape. It just sits there. It's fixed. It's locked in a certain pattern. Okay, now I take the water and I heat it up and I boil it. Which one is more orderly? The liquid water or the steam? The liquid water. Even though this is less orderly than the ice, it's at least got a certain volume. It's sitting in the beaker. But I heat it up and start boiling it and evaporating it, and all of a sudden, again, it's like herding cats. The water molecules are all going everywhere. They're gone. They're all over the place. So there's a higher degree of randomness, a higher entropy. This has a higher entropy than this. And then our ammonium nitrate, if we went back to our ammonium nitrate example, here's our ammonium nitrate crystals, here's our water. I pour the water in on the ammonium nitrate, and what happens? That nice little crystal pattern is busted up now to this random ammonium nitrate ions floating all around in the water. So every one of these, so all of these have a positive change in entropy. What's happening to the entropy? Increasing. Entropy is increasing in those processes. Keep in mind that we're always moving from the left to the right here. Conversely, to go from the right back over to the left, entropy would be decreasing. Delta S would be negative. To take liquid water and freeze it into ice is going to reduce the randomness. All right, so that's good enough. Well, you can get involved in a lot of different discussions about and trying to predict whether a reaction or a process is going to occur spontaneously or not. I'm not going to get into that. Here is the granddaddy of them all equations right here. This relates something we call Gibbs free energy. It ties together enthalpy and entropy and temperature in Kelvin, the absolute temperature. And that is the bottom line thermodynamic equation, that the change in Gibbs energy is equal to the change in enthalpy minus the temperature times the change in entropy. Some reactions will be driven by the enthalpy change. Some reactions will be driven by the entropy change. And like I said, temperature may be the pivotal point there. You can mix gasoline and oxygen together and nothing happens at room temperature, but at 600 degrees centigrade, they're going to spontaneously explode. Well, you got this temperature term in this equation. And so that has an effect. You can't necessarily say, oh, that's not a spontaneous reaction, that it will never be spontaneous. It isn't under those conditions. Under other conditions, it may occur spontaneously. And you can come back and look at this slide. You know, if the enthalpy change is positive, the entropy change is negative. Delta G is always positive regardless of T. Temperature may determine the direction of spontaneity, whether something's spontaneous or not. But I won't be driving this. Let's see, which reaction is spontaneous? We won't go into that too much. But here's the better one on entropy. Entropy. Here is, there's some order here. This is all our alphabet. So 26 letters, some of them capital, some of them lowercase. but they're random, and you can't read this. High entropy. This is a high degree of disorder, but you rearrange those letters into words and punctuation, et cetera, in the right order, in a certain order. There's low entropy here. The entropy has decreased, and you have high information density, low entropy. Low information density, high entropy, or high degree of randomness, low degree of randomness. Okay, let's shift now to calorimetry. And this is coming off of this word. All right, so where are we getting this calorimetry? Calorie, and when you look at a food label and it talks about calories, it's really talking about what is the heat value of this food. How much energy is in this food? What is the amount of energy in this food? And let me just mention calorie for a minute. There's a lowercase calorie. Amount of heat required. 1 calorie is the amount of heat required to raise 1 gram of water 1 degree centigrade. Okay, that's not hard to remember. There's all ones in there. So 1 calorie equals the amount of heat to raise 1 gram of water 1 degree centigrade. And that has a lowercase c. The nutritional calorie has an uppercase C. Is simply 1,000 calories. 1 nutritional calorie. So if you look at a granola bar and it says the calories, it should, or any food, it should say when it has the calories, it's capitalized the C. It's capitalized because it knows there's a difference between a capital C calorie and a lowercase c calorie. A lowercase c calorie is not a lot of heat. It's a really little bit of heat. 1 gram of water is 1 milliliter of water. I mean, it hardly wet your palm. So it's the amount of heat necessary to raise that 1 gram of water 1 degree centigrade. That bottle back here, there we go, there we got it. 500 milliliter bottle of water, 500 grams of water would take 500 calories to raise that bottle of water from 20 degrees centigrade up 1 degree to 21 degrees centigrade. Take 500 calories to move that up 1 degree centigrade. Your body is a lot of grams of water. I mean, if you just said you were all water, it's thousands of grams of water, 450 grams per pound. So it takes a person roughly 2,000 calories to get through a normal day. Depending on your size and your metabolism, but it might go from 1,700 to 2,200 calories. I don't know what that range would be, but that's the amount of heat you need to keep your body temperature up where it is. All right, so calorimetry, this is kind of going back to those pictures where I said a thermochemist or a physical chemist would look at a system and the effect on the surroundings. Here is a little device, simple little device, to kind of isolate a reaction inside the calorimeter and insulate it from the room around it so that if there is heat released, it doesn't just completely release out into the room right away. What's it do? It's contained in the calorimeter and makes the temperature of the thermometer go up. And you can see what the change in temperature is as a result of what happened inside the calorimeter. Let's do a couple calculations, or one at least. So here is your calorimeter equation. Q is heat. The amount of heat involved there is going to be the mass of material inside the calorimeter times the change in temperature inside that calorimeter times the specific heat of the material. Different materials have different specific heats. Typically here, we're talking about water, the specific heat of water. Because a lot of times we're doing reactions in an aqueous solution. So we talk about the specific heat of water. All right, let's get an example here. Calculate the amount of heat needed to heat 27 grams of aluminum from 25 degrees centigrade to its melting point of 660 degrees centigrade. Now here, the specific heat of aluminum, in this particular case, we don't have water, we have aluminum, so we have to work off of the specific heat of aluminum, which is 0.215 little c calories per gram per degree centigrade. That's aluminum. All right, so we're heating up 27 grams of aluminum. Times the specific heat of aluminum times the change in temperature, delta T. So the final temperature is 660 degrees centigrade. The initial temperature is 25 degrees centigrade. So what is the delta T? Delta T is the difference between those two numbers. (635 degrees centigrade). Now look at, here's your grams, here's your degrees centigrade, and we're going to get Q in calories. And what is that going to be? I'm getting something like 3,686. Is that right? Let's just round that off to 3,690 calories. That's what Q is. Okay, that is the amount, let's see, the amount of heat needed. So this aluminum is not going to go up in that temperature spontaneously or by itself. It's going to sit there at room temperature unless we do something. So what do we have to do? Are we adding energy or are we releasing energy? Is energy being added or released to the aluminum to heat it up? Adding energy. If we didn't add any energy to it, it would not get hotter. There's no reaction going on here. All we're doing is heating the aluminum. But this is telling us how much energy it would take to heat a chunk of aluminum, 27 grams. That keep in mind, that's about a mole of aluminum. 26.98 grams per mole. Round that off. 27 grams of aluminum. That's about a mole of aluminum. It would take 3,690 calories to heat it up to that temperature. So, yeah, so that's basically calories per mole, actually, right there. But, all right, so this is endothermic. We're heating the aluminum. Here's another example here. We're taking an acid, reacting it with a base. We're pouring the acid and base together in a calorimeter. The total mass of the acid and the base, M equals 150 grams. We've got concentrations up there, but that's not our mass. That's just how concentrated those solutions are. But, and how much, no, that's how much of it. We're taking 1/10 of a mole of HCl, 1/10 of a mole of KOH in water that weighs 150 grams. Water, HCl, KOH all weigh 150 grams. And we're going from 25 to 29.4. So delta T equals 4.4 degrees centigrade. Now what they're working off of right here is the specific heat of water. This is the specific heat of water. I told you it takes 1 calorie per 1 gram per 1 degree centigrade for water. That's taking that definition and just putting it into a term that is specific heat. Okay, is this reaction endothermic or exothermic? How would you figure that out? It's what? How do you know it's releasing heat? Yeah, that is what it means. What in the data here indicates to you that it is releasing heat? You're right. Okay, the change in temperature is doing what? What's happening in temperature? It's increasing. What is causing that temperature to increase? The reaction that's going on here. The HCl is reacting with the KOH, and there is heat being released. Where? Into that water where the reaction is occurring. The reaction is occurring in a solution of water, and it's making the water go up in temperature, 4.4 degrees centigrade. So yes, it's exothermic. If you mix two things together and it gets hotter, it's exothermic. Something is releasing energy. If it gets colder, it's endothermic. Okay, so it's exothermic. And I won't dwell on it, but here's the data. Here's the 150 grams. Total mass, it's in the calorimeter. The specific heat of the environment in there, this is an aqueous system, so we're using the specific heat of water, and there's your delta T, 4.4 degrees centigrade. And you get 660 calories. .660 calories of heat has been released. Okay, now what would be the energy evolved for each mole? So for 1 mole of HCl. Well, we're getting 660 calories corresponds to 1/10 of a mole of HCl. How do we know that? told us right there. We reacted 1/10 of a mole of HCl, and we released 660 calories of heat. Okay, so then if you take that 660 calories divided by 1/10 of a mole, you get 6,600 calories per mole, or 6.6 kilocalories per mole. If I had 6,600 calories, 1 kilocalorie per 1,000 calories, that would be equal to 6.6 kilocalories. Okay, I'm not going to, again, some of these things I'm going to just point out to you. There is a relationship between calories and joules. Those are two different units for energy. Just like centimeters and inches are two different units for length, 1 calorie equals 4.184 joules. All right, so there are two different terms, two different units we can use for energy. So I won't dwell on that. They're just converting the 6,600 calories to joules. All right, so before we leave that topic, let me just say, be familiar with that equation. Learn that equation. Q, and Q really is H. In the aluminum case, let me erase that. In the aluminum case, it's Q. It's just heat. We're just saying, it took some heat to heat up this aluminum. How much heat? And we calculated the heat necessary. But whenever we get down into a chemical reaction, we could actually say this Q of the reaction, we are talking about enthalpy. What are we talking about? We're talking about heat energy changes associated with a chemical reaction. That's enthalpy. H. So whether we're talking about Q, or we could really be talking about the change in enthalpy. This is the enthalpy change from reacting 1/10 of a mole of HCl. And then down here we would have the enthalpy change per mole of HCl. All right. Okay, there's two more topics. Kinetics, I think there's two more. Kinetics and equilibrium. You guys all right? Yeah, you had an exam. I mean, this borders on abuse, okay? I understand that. I mean, I was a student once. Actually, we're lifelong learners, right? I'm signing up for a graduate course I'm going to take online starting in August. I'm going to try to start boning up for it. So I'm going to really be in your shoes. Just trying to take another course. But yeah, I know your brain's fried from the exam, and now it's being fried from thermodynamics. When I went to university, chemistry majors, there'd be cars running around with little bumper stickers that said, honk if you passed P-Chem. All chemistry majors had to take physical chemistry. And if you were an organic chemist, inorganic chemist, analytical chemist, the last thing you wanted to take was physical chemistry. But you had to. It was required. It was a requirement, 1 year of physical chemistry. And there were some people that could not become chemistry majors because they couldn't get through P-Chem. So it was honk if you passed P-Chem. You guys have bumper stickers. Honk if you passed 1305, right? So, all right, kinetics. All right, thermodynamics, all of what we've talked about so far today since the exam has dealt with thermodynamics. Determines whether a reaction can occur. But it tells us nothing about whether it will occur or how fast it will occur. Okay, gasoline, we've been talking about that. You add a spark to gasoline, what's the kinetics? Is it fast or slow? Does that react fast or slow? Fast. if you add oxygen to iron, the iron on your car, and produce rust, is that kinetics fast or slow? Slow, fortunately. Fortunately, it doesn't go as fast as gasoline. Otherwise, you drive off the lot and you've got a pile of rust. Okay? It rusts, automobiles rust very slow. So rust at room temperature and our conditions we have is slow kinetics. And gasoline is high kinetics. Now, one thing we won't talk too much about at all, but I'll just mention it. If you took sophomore level organic, you would get in the 1307 organic chemistry. We'll talk about reactions, but it won't get into the real nitty-gritty of mechanism. But in sophomore organic, you get into the mechanism. What's the first thing to happen if methane reacts with oxygen and you've got these bonds and you have these bonds? The mechanism asks, okay, what happens first? Does the oxygen bond break? Does a carbon-hydrogen bond break? What goes on here? And they would actually go down through the mechanism, and oftentimes you would find for this to go over and form these bonds, and what are we going to get? This bond, these bonds, look at that, you don't have these over here. They would actually have 6 or 7 steps that are taking place. First thing that's happening is this is breaking. And you've got a carbon with 3 hydrogens on it, and you've got a hydrogen. I don't know what the mechanism is, but this is what mechanism talks about. What are the exact specific steps that get you from here to there? That's mechanism. Kinetics is how fast does that happen? How fast? What is the kinetics of it? I'll ignore that one. This is, well, okay, just real quickly. Here's at the beginning of the reaction. Usually down here on this line is time, seconds. It could be seconds, minutes, hours, months, years. Depends on what the kinetics are. If the reaction is going to take place in a minute, then you're going to measure this in seconds. 10, 20, 30, 40, 50, 60 seconds. You start out with all of A and no B. So A is black, B is red. And what's happening as a function of time? You're starting to produce some red. More red, more red, more red, and you almost completely, you still have a little bit of A around, but a lot of B. And so so you can have a rate. You can actually have an equation for the rate of the reaction. What is the change in the concentration of A as a function of time? There's a negative, it's decreasing. That's going to equal the change in the concentration of B as a function of time. That's positive. So as A is disappearing, B is appearing. Okay, now let me give you a little example. Here's bromine. Does it say what it's in? I could guess what it's in. It's bromine in, let's say, hexane. So we got bromine sitting here in hexane, and bromine is orange. It is it's reddish orange. And bromide, bromine is reddish orange, but the carbon bromine bond is colorless. This is colorless. So, and this is what a kineticist would do. Someone studying rates of reaction, they'd say, okay, what reaction do I want to study? What is it I could monitor? Is there an instrument I could use? Is there some observation I can make that would track the progress of this reaction? Color. In this particular reaction, it's color. It isn't always, because not always are you dealing with something, one of the reactants that does have color. But bromine has color, and you can see the bromine disappearing as a function of time. All right? And so if you had not a calorimeter, but a colorimeter, and there are colorimeters, that measured the intensity of this color coming out of a solution, you could actually follow this reaction as the reddish-orange color disappeared. And you say, okay, this is the rate of that reaction. Okay, what more do I want to say about that? That's probably good enough. Here's a concept that's worth, and another term that you should kind of put under your belt: activation energy. A moment ago, about 20 moments ago, we focused on this, and we were saying this was our change in energy or our change in enthalpy. We can kind of use those interchangeably. We had methane plus oxygen forms carbon dioxide and water. So we had, where are these energy-wise? Where are the products energy-wise? What's the difference? Every reaction, any reaction, has a certain amount of activation energy. There's a hump you have to get over to get that reaction started. All right? So there's a barrier, irrespective of this energy. There's another bit of energy that needs to be supplied to get the reaction started. All right, I won't use any names, but your alarm goes off in the morning, and there's a certain amount of energy needed. It happened to me too this morning. Somehow I was sleeping really well. The alarm was going off for a little while. I thought, what is that? I finally realized, oh, that's my alarm. So there was a certain amount of energy I had to turn that baby off, and a certain amount of activation energy to throw your feet off over the bed and get up, right? You're awake, but you're not moving yet. Activation energy. There's in a physical sense, I could push on it. I'm pushing on this, but nothing's happening. But at a certain point, I overcome the friction between that and the table, and it starts moving. And the original force I was pushing on it actually now is moving it, because I've overcome the friction. There's a barrier to get the thing going. You follow me? That's what you have in chemical reactions too. Activation energy. You even have it in an endothermic. That example I showed you there was exothermic. It's going to release energy. Even in an endothermic example, again, there is well above this energy you need, that is needed to get the products to form. There is a barrier that has to be overcome to even start getting to product. Activation energy. Minimum amount of energy required to produce a chemical reaction. Okay, there are a couple of variables that affect rates of reaction. Concentration is a big one. Remember, the kinetic molecular theory said molecules are in constant motion and they collide with one another randomly, and only the effective collisions result in a reaction. Okay, so if I increase concentration, let's say I have a flask or I have a container over here and I have 4 molecules in there. I have another container over here, same reactants. I have thousands of molecules in here. Thousands. In which container are there more collisions between molecules? Second one. So this is higher concentration, more collisions. All All right, so whenever we increase concentration, we are increasing the number of collisions. And if now there's enough energy for the collisions to go on to produce products, we're going to have a faster rate of reaction. Okay? If the collision's only happening once every 5 minutes, there's a collision, we got a very small reaction. But if there's thousands of collisions every second, then you got a much faster reaction. So concentration affects rate of reaction. Okay, next, temperature. So this is one thing that affects the rate of reaction. What does temperature do? All right, temperature is the energy of the molecules is directly proportional to its energy. You lower the energy, the molecules are kind of lazy and they're just moving around, they're bumping into each other. Remember we said effective collisions cause a reaction. So you raise the temperature and all of a sudden, bam, 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 and they're not just they're hitting harder. Okay? Hitting harder. So if they're hitting harder, they're hitting with more energy, there's more likelihood that there's enough energy that's going to break bonds and lead it to reactions. I like my San Antonio 1604 example here. All right? Saturday morning, 5 a.m., you get on 1604. There are very many cars there? No. The concentration of automobiles is low, so the likelihood of a collision, let's say 6 a.m., so it's getting light. The likelihood of a collision is low. You don't hear a lot of traffic reports at 6 a.m. on Saturday morning. They just don't have them. Concentration is low. Accident rate is low. All right, you get on Friday afternoon, and the traffic report is 5 minutes long. But here at this location, that location, that location, and that location, they're clearing up accidents. Okay, now let's say everybody's traveling at 55 miles an hour versus everybody's traveling at 85 miles an hour. So temperature, that's your temperature thing. If you do have an accident at 55 miles an hour, it's a little fender bender. You have an accident at 85 miles an hour, and it's a really pretty uproarious accident. Okay, so temperature is increasing the energy. Physical state. Solid state reactions are hard. It's hard to get two solids to react with each other. Gaseous state, they're free and moving, they're bumping into each other. That's a good place to get things to react. So in the cylinder of your automobile, the gasoline is being vaporized. It's in a gaseous state with air there, and liquid state, they're listed more mobility in a solution. And then this is where catalyst, I'm going to put here enzyme. All right, when you get into Chemistry 1307, we spend a chapter on enzymes, which are biological catalysts. That's what enzymes are. Protein molecules. And what do catalysts do? What do enzymes do? They decrease the activation energy. So this is the activation energy for this reaction. The catalyst lowers that so that there are more molecules that are able to get over this hump, and it speeds up the reaction. So catalysts speed up the reaction without taking part in the reaction. They're just used over and over and over and over again. So they're there in a very minor component, but they speed up the reaction. Let's see if I have enough time to do equilibrium and Le Chatelier's principle. Let's try it, because your homework will probably mention this. Let me contrast. Here we're talking about equilibrium. Let me just contrast it with hydrochloric acid. You've seen me writing things like this. If you take HCl and bubble it into water, it dissociates, doesn't decompose. It's dissociating into hydrogen ions and chloride ions. And I draw a firm arrow to the right saying that there really isn't an equilibrium. All of this is converted to ions. All of it, 100%. So there isn't any of the ions colliding back together and HCl being formed. But if we to take this is acetic acid, this is the acid in vinegar. This is a different acid, this is a weak acid. You end up with an equilibrium where all three of these things exist together. If we have this in water, you're going to have these molecules, you're going to have these ions, and you're going to have these ions all floating around in the water. All three things. And what is the first one? That is a molecule. That is the original molecule, and then you have these ions. And you can see that I'm drawing an arrow like that, and I'm drawing an arrow going back in the reverse direction. And we would say this is a dynamic equilibrium. It's not that you put it in there and 1% of them dissociate and then everybody just is happy and nothing else is happening. What do I mean by dynamic equilibrium? Whenever an H plus collides with a CH3COO minus, it forms a molecule. And when enough of those do that to form that molecule, some of the molecules dissociate to form the ion and the H plus. Okay, so it's dynamic equilibrium. I like to get practical examples. LOH building. Let's say at 10 o'clock we reach an equilibrium, that there's 800 students, 800 people in this building. Okay, at 10 o'clock? And we're kind of at a plateau from 10 to 2, 800 people. Are they all the same people? No. You stand down there and watch. You see 3 people come out of the building. You see 3 people go into the building. You see 3 people come out, 3 people come in. Okay? That's a dynamic equilibrium. We have the same concentration of people all the time from 10 to 2, roughly. But there are people leaving, there are people coming at a constant rate. The rate at which people are arriving at the building equals the rate at which people are leaving the building, and we have a dynamic equilibrium. That's what I mean by that. So that's what's going on here. You end up with a constant concentration of molecules, positive and negative ions. They reach a steady concentration, but they are not necessarily the exact same ions and molecules during all that period of time. So this is an equilibrium, and there are many things like this, and you can actually write equilibrium constants. And they're coming off of the kinetics. The rate at which acetate ions are bumping into hydrogen ions and the rate at which the acetic acid molecules are decomposing, that's the reverse rate, forward rate. You get a equilibrium concentration. So the rate at which they are forming, the rate at which this is forming that, is equal to the rate at which this is dissociating into that. And you get a equilibrium constant. Okay, Le Chatelier's principle. I don't think I can do that in a minute. Le Chatelier's principle, let me get to the bottom line. Here it is. If a stress is placed on a system, now you could just talk about a system in general, but a chemical system at equilibrium, the system will respond by altering the equilibrium in such a way as to minimize the stress. And probably the main stress I would like you to understand is concentration change. So here's an equilibrium. Here's the iron. That's the color of it. Here's the well, maybe I can't do this. But if you had this equilibrium and you added iron to it, let's say you added iron. How would you do that? You could drop in some ferric chloride. That would give you iron plus 3 ions. It is going to raise this concentration. And what the system will do is move towards making more of this in order to bring this back down, to lower that stress. So it sees that increase in iron concentration as a stress on equilibrium. And what does it do? It shifts to the right to make more product, because that will use up some of this and bring the concentration back down to a closer to what it was originally. That's Le Chatelier's principle in a nutshell. Okay. It would do you well to get familiar with the pH scale, pH. Bring a calculator with a logarithm function on it, and bring the calculator you want to use in the exam. Because we're going to do some logarithmic calculations, and you're going to want to use the same calculator. So don't just come with your cell phone. Come with a calculator you can use in your exam. And I'll see you Thursday. Very good. You underwent the abuse very well this morning. I think.
I'm looking and it says that chapter 7. Oh, never mind. I'm crazy.
No, you're not.